What if everything we thought we knew about the dance of celestial bodies was just the beginning? Imagine a universe where planets whirl in intricate patterns, their paths dictated by the invisible forces of gravity. In this vast cosmic ballet, every orbit tells a story of motion, balance, and the relentless pull of the unseen. As we embark on this exploration of planetary orbits, let's delve into the fundamental forces that govern these majestic trajectories. At the heart of it all lies gravity, a force so pervasive that it shapes the very structure of our universe. But gravity is not just a simple attraction. It is a complex interplay of mass and distance, a relentless force that binds planets to stars, moons to planets, and galaxies to one another. Picture our own solar system, a swirling mass of planets, each tracing its own unique path around the sun. The sun, a colossal ball of fiery gas, exerts an immense gravitational pull, keeping the planets in their orbits. But why do these orbits take the shape they do? Why are some circular, while others are more elliptical? To understand this, we must journey back to the laws of motion articulated by the brilliant minds of history. Enter Johannes Kepler, a man whose observations of planetary motions would change our understanding of the cosmos forever. In the early 17th century, Kepler formulated 3 fundamental laws of planetary motion, each unveiling a layer of the intricate mechanics at play. His first law states that planets move in elliptical orbits with the sun at one focus. This revelation challenged the long-held belief in perfect circular orbits and opened the door to a new understanding of how celestial bodies interact. Imagine a planet like Earth tracing an elliptical path. At one point in its journey, it is closest to the sun. This point is called perihelion. At its farthest, it reaches aphelion. But what drives this elliptical shape? The answer lies in the gravitational forces and the inertia of the planet as it travels through space. As a planet moves closer to the sun, it speeds up, pulled by the sun's gravity. As it drifts away, it slows down, illustrating the delicate balance between gravitational pull and the planet's momentum. Kepler's second law, often referred to as the law of equal areas, tells us that a line drawn from the sun to a planet sweeps out equal areas during equal intervals of time. This means that a planet moves faster when it is closer to the sun and slower when it is farther away. Imagine the thrill of watching a planet race across the sky, faster and faster as it approaches the sun, only to slow down and take its time as it journeys away into the cold vastness of space. What about Kepler's third law? It relates the time a planet takes to orbit the sun to its distance from the sun. The square of a planet's orbital period is directly proportional to the cube of the semi-major axis of its orbit. This law allows us to compare the orbits of different planets. For instance, while Earth takes 1 year to complete its orbit, Jupiter, being farther from the sun, takes nearly 12 years. This relationship not only illustrates the harmony of the solar system, but also serves as a foundation for understanding the orbits of exoplanets around distant stars. However, the story of planetary orbits does not end with Kepler. The gravitational interactions among multiple bodies can complicate these paths, leading to fascinating phenomena. Consider the case of our moon, which not only orbits Earth, but also influences the tides and stabilizes our planet's axial tilt. The gravitational tug-of-war between Earth and the moon creates a delicate balance, one that keeps our planet in a stable orientation as it orbits the sun. As we expand our view to other star systems, we find that planetary orbits can be influenced by more than just the gravitational pull of a star. Consider binary star systems, where 2 stars orbit a common center of mass. The gravitational influence of both stars can create complex orbital dynamics for any planets that may exist within the system. These planets may have highly elliptical orbits, or they might even be ejected from the system entirely if gravitational forces align just right. But what about planets that exist outside our solar system? The discovery of exoplanets has revolutionized our understanding of planetary orbits. Some exoplanets orbit their stars in ways that defy our expectations. Hot Jupiters, for instance, are gas giants that orbit very close to their stars, completing an orbit in just a few days. This challenges our previous notions of how planets form and evolve. The gravitational interactions in these distant systems can lead to chaotic orbits, where planets are captured or ejected based on the gravitational ballet of nearby stars. Now, let's turn our attention to the concept of resonance, a phenomenon that occurs when two or more orbiting bodies exert regular, periodic gravitational influence on each other. This can lead to stable configurations, as seen in some of the moons of Jupiter. Io, Europa, and Ganymede, for instance, are in a resonance known as a Laplace resonance, where their gravitational interactions maintain their orbits in a stable pattern. This fascinating dynamic not only highlights the complexity of orbital mechanics, but also raises questions about the potential for life in these icy worlds. As we ponder these complex relationships, we must also consider the role of perturbations, small changes in the motion of a celestial body caused by the gravitational influence of another body. These perturbations can lead to long-term changes in the orbits of planets and moons, such as the gradual shifting of Pluto's orbit due to the gravitational pull of neighboring bodies in the Kuiper Belt. Understanding planetary orbits is also essential for space exploration. As we send spacecraft to distant worlds, we must carefully calculate their trajectories to ensure they reach their targets. This requires a deep understanding of the gravitational forces at play, the orbital paths of both the spacecraft and the planets, and the timing of launches. The intricacies of orbital mechanics come into play in every mission, from the Voyager probes that have traveled beyond our solar system to the Mars rovers that navigate the red planet's surface. But what lies ahead for our understanding of planetary orbits? As we develop more advanced telescopes and technology, we are beginning to glimpse the orbits of planets around distant stars with unprecedented clarity. The research into gravitational waves also promises to shed light on the dynamics of planetary systems, as we learn to detect the ripples in spacetime caused by massive objects in motion. Each discovery brings us closer to unlocking the mysteries of how planets are born, evolve, and interact within their cosmic neighborhoods. As we reflect on the incredible dynamics of planetary orbits, we are reminded of the beauty and complexity of the universe. Each planet, each moon, each comet has its own unique story, woven into the fabric of space and time. The dance of the celestial bodies inspires wonder and curiosity, inviting us to explore further and ask deeper questions. What happens when a rogue planet is ejected from its home system? Can we ever truly understand the vastness of space and the forces that govern it? Each question leads us down a new path of discovery, a new orbit of thought that expands our understanding of the cosmos. As we conclude this journey through the dynamics of planetary orbits, we invite you to reflect on the wonder of the universe. The intricate dance of celestial bodies is a reminder of the mysteries that still await us, mysteries that challenge our knowledge and ignite our imagination. What's next in our quest to uncover the secrets of space? Stay tuned for more explorations into the wonders of the universe. Don't miss out. Subscribe now and join us as we continue to unravel the mysteries of the cosmos, one orbit at a time.